Yeah, I thought I would try to kind of at least get 4.3 number 7 started. This is 2018, and we actually only had 2 people in class, and we did this. I'm going to go ahead and make a video just to, at least get you going on it. We may not have enough time on the video to work the whole thing. The algebra gets kind of long, and it's kind of, we'll try to at least get to started on it. Now, they want us to basically evaluate this integral, and they want us to do it by taking the limit of the sum of all the rectangles that we could draw to approximate this area. I've kind of drawn a sketch over here. We're looking at the area between 1 and 2. So that's going to mean we're going to need to kind of tweak some things. If we want to try to figure out how to write the sum of n, like we were doing in 4.2, we need to think, okay, first of all, I'm going to divide all these up into, all these little rectangles, they'd be in here, and I can make them skinnier and skinnier and skinnier. And so how could I describe the base? Because remember what I do, just for a minute, we're going to we'll do the limit at the end, but let me go ahead and try to write S of n. Because we know there's all kinds of simplification that has to happen there. We know we're going to add up an infinite amount of rectangles, or we're going to divide it into n rectangles at first, but then remember when we take the limit, that'll mean we're going to basically say we want infinite rectangles. So what I really need here is I need to represent the rectangles by saying what's the base times the height. Okay. Now if you look at what's going on here, how could I describe the base of the rectangles? Where if you remember how we calculate that is we say, okay, we're going to end at 2, and we started at 1, and I'll decide how many rectangles I want to split it into. We call that number of rectangles n. All right, well that would be 1 over n. So when I do the sum, that actually represents my my base. Okay, so each rectangle is 1 over n. One of the points that this section makes in the book is that actually the rectangles don't have to always be the same width on the base. They could be different widths, but as we let the number of rectangles approach infinity, even if we've got one that's a lot larger than the other one, it will actually, as we create these infinite rectangles, it'll approach 0 as well. So it kind of really doesn't matter if they're all the same size. And so let's see, we're going to do the sum of I equal 1 to n, and if you remember what I had been doing in previous things is I had been factoring out that 1 over n out front. I'm not going to do that this time just because the algebra on this I think in this case I ended up putting it back in just because it seemed to be easier for me to deal with. Now how am I going to describe the height? Well, the height is the y value at each on the curve, right? For each rectangle, it's what was the y value, which actually is a function value. Well, how can I describe that? If you remember when we're doing sum, it's kind of like doing for loops in computer science where you're indexing through and you're looking at your first rectangle and then your second rectangle and your third rectangle. We end up looping to infinity when we take the limit. But what our goal is to rewrite this with that summation notation. So we need to kind of figure out how am I going to describe my height here, and it's given by this x squared plus 1 over here. So it's x squared plus 1, but how am I going to describe the x's I put in? Well, each rectangle is 1 over n, but if I want to kind of figure out where I'm at, I've got a little bit of a different issue here. I'm going to write in green for a minute. I don't start at 0 anymore like some of the previous ones we had in 4.2. I'm actually going to start at 1. And how am I going to describe how far over I have gone, for the, basically the x value that I want to find the y value for in the function to find its height? Well, if I were going through the first time, it might be 1 over n, but the second time I go through, it might be 2 over n, and the third time would be 3 over n, and the fourth time would be 4 over n, and the fifth time would be 5 over n. And so how I describe that is I over n, and we had that in our previous section that we would describe it that way. What's different here is instead of just saying I over n, I have to say it's 1 plus I over n, because if you look up here, I'm starting at 1. So this is basically the x I'm going to plug into the function value. Well, so I got to come over here. This is 1 plus I over n, and it's not showing up very well, squared plus 1. So that's what I'm going to put over here, but let me go ahead, and I'm going to draw a little line here. Not a lot of room here. As a matter of fact, it's not going to fit in there when I get done. Let me go ahead and multiply this out, though, and then that's what I'm going to write in here, and I'll be ready to at least simplify my sum. So the goal for the minute is to figure out what I need to write in there, and I'm going to have to simplify. This is this x squared plus 1 right here. This is the x squared plus 1. So I actually have to think of it this way. It's a lot more than you might think. I have to multiply 1 plus I over n out. No, I'm good. Okay, let me keep going. I thought I had stopped the counter. I thought I had paused the video, but it doesn't look like I did. All right, so I've got to square 1 plus I over n and then add 1. Well, if you distribute this out, I'll do that in a different color. 1 times 1 is 1. 1 plus I over n is I over n. But then I have another I over n times 1, so there's another I over n. And then I over n times I over n is I squared over n squared. And then I got this plus 1 on the end. Well, if I simplify this and kind of put the like terms together, 1 plus 1 is 2. 1I over n plus another I over n is 2I over n. And then I've got plus I squared n squared. So this is going to be what I got to put in this place where now I'm scribbling in blue. Let me go to a new slide because I'm going to run out of room. Okay, so I went ahead and copied that down here. Now what I'm going to do, I used to a lot of problems in 4.2 factor that 1 over n out, but I got so much stuff that I'm going to have to factor out. I think it's just going to be easy for me to distribute first. So if I go ahead and distribute this 1 over n, remember that's the base. Each rectangle has the same base in our thinking here. That's going to be 2 over n plus 2I over n squared plus I squared over n cubed. Okay, now what I'm going to do, I'll try to do as much as fit on the video, but it will time out, so there's no way I can work all of it. So what I'll do is I'll give each one of them their own sum. I equal 1 to n. Let's see, of 2 over n. Let me go ahead and say, let me put the 2 out front and the n, and really, remember, I just want i's isolated, so if I don't have an I, I'm just going to write a 1 on this first one here. Let me circle it. This is the one I'm doing right now. Now, I'll kind of color code this. Now I'm going to add in the next, I'm going to give the next one its own sum. I equal 1 to n. But what I can factor out of it is 2 over n squared. And what would be left would be the I. Remember, I'm trying to always get that I isolated. All right, and then like for the last one, it gets its own sum, 1 to n. And I'm going to factor out 1 over n cubed for it, and that leaves me an I squared. So if I do this, now I can start going and using my summation formulas that we had in section 4.2. So the sum of 1 to n of 1 would mean you're adding 1 together n times. That's actually n. And then 2 over n squared, there was a formula for this I part right here. That was n times n plus 1 over 2. And then 1 over n cubed. There was a formula for I squared. It was n times n plus 1 times 2n plus 1 all over 6. So now I'm going to reduce. And once I get this reduced, then I can actually go take my limit. It's just so much algebra. We usually put that limit on at the end. So these would cancel out. And so what I'm going to end up doing is taking the limit as n approaches infinity. I'll go ahead and add that in now. That's going to be 2. And then over here, let's see. Let's do some canceling out. N goes into n one time, and n goes into n squared, or n squared take out of n would be n. These 2's would cancel out. So what I end up on top with is 1 times n plus 1. So that's n plus 1 on top, and on the bottom I have n. And then over here I could say this n goes into that n one time, and if I take one n out, I've got n squared left. So I have, let's see, I have n plus 1 times 2n plus 1. Let's go ahead and distribute that. It's all going to go over 6. So n times 2n is 2n squared. N times 1 is n, but here's another 1 times 2n is 2 more n, so that would be 3n. Again, I'm just distributing or foiling. And then 1 times 1 is 1. All right, so now the next step would be let's split these up into separate little, things to take limits of, or separate fractions. Okay, so I'm not going to take the limit yet, but this is going to be n over 2, n plus 1 over 2. Oops, I kind of noticed I made a mistake up here. Some of you might have noticed it. The 2's canceled out. This actually is an n left. Right, this n right here is an n here. So I was kind of thinking something didn't look right. So I'm going to, if I split that up, that's going to be a n over n plus a 1 over n. Okay, now let me go to that last fraction. I'll do it in kind of a purple color. This is going to be 2n squared over 6. I'm just splitting this each fraction up, plus 3n over 6 plus 1 over 6. Oh my gosh, and what did I forget here? I forgot the n squared there, so I need to write that down. It's hard to read for me, some of this stuff, once it's written on the iPad. Okay, so let's try to reduce all of that. Let me kind of simplify all this stuff up. Let me go to a new slide. So hopefully you've been just keeping up with your the work and writing it down as we go. So if I go ahead and reduce this, again the video is going to cut off pretty soon. I've got the limit of 2. N over n becomes 1. 2n squared over 6n squared becomes let's see. Oh, I forgot the 1 over n. There's a 1 over n there that just stays. The 2n squared over 6n squared becomes a third. The 3n over 6n squared becomes 1 over 2n. And then the last term is just 1 over 6n squared. Now there's some numbers here we can go ahead and add together, and they're actually going to give me, there's 2 plus 1 is 3. And then there's a third, so it's 3 and a third. That takes care of these and this. Now if I take the limit and I plug in infinity, 1 over infinity, this one right here would become 0. Already took care of this guy. 1 over 2n would basically become 0 because you'd have an infinity in the denominator, and this other one would be 0. So you'd be adding all these zeros in. So the answer is just 3 and a third, which is 10 thirds is the way the book writes it. And we're done.